number. And frankly, he says, I don't believe in this number. Okay, so this is like Brouwer or Kronecker in a way, or intuitionism. It's sort of a constructive view. And he said this number really looks illegitimate. Okay, so that's 1927, which is interesting. Now, the next step, I would say, on the argument that the arguments I'm collecting against the real number, mathematical arguments, is Turing's 1936 paper. Turing, 1936, introduces this beautiful notion. It's not about the holding problem. Turing's original paper is about real numbers. The title is On Computable Reals with an application to the Entscheidungsproblem. But let's just talk about computable reals. You know, a real number, having a very primitive point of view, is just an infinite number of digits, right? 0 point or comma 13549, 3.14159. Let's forget about the integer part. So you look at this infinite sequence of digits, which is the fractional part of a real number, and Turing says, well, it's possible there's an algorithm to compute the digits one by one, and it's possible there is no algorithm. And he's able to show in his first paper that a lot of things, like algebraic numbers, for example, are computable. He makes most real numbers you encounter in analysis are computable, pi, e, everything else. But Turing uses Cantor's diagonal argument to show they're uncomputable real numbers. He diagonalizes, you see, all the computable reals are countable or denumerable because the computer programs are countable, denumerable. You use Cantor's diagonal argument and you diagonalize over the computable reals, you get an uncomputable real. But there's a more interesting argument that Turing doesn't have in his 1936 paper, which I'd like to show you. I mean, to me it seems sort of obvious, but I don't know if I read it anywhere else. There's a measure theory argument. The measure theory argument, which I got from Curran and Robbins' What is Math, applied to Cantor's diagonal argument for set theory to show that the reals are more numerous than the whole numbers. Well, let's apply it to computable reals. If you look at all possible computer programs, they're countable. So you put an interval of, you can cover the first computable real with an interval of size epsilon over 2. The second computable real you covered with an interval of size epsilon over 4. The third with epsilon over 8. If you sum the total length of this cover, the total length is epsilon, and I have a covering. I take the unit interval from 0 to 1, and I'm trying to cover all the computable reals. And I can make this cover as small as I like. I'm just proving that the computable reals, because they're countable, are a set of measure 0, which means they have 0 probability. Because I can cover all the computable reals with intervals whose total length is as small as I want, but the unit interval of real numbers from 0 to 1 has unit length, right? And I can cover all the computable reals with intervals that I can make as small as I want. Therefore, if I pick a real number at random, I close my eyes, and I have a very sharp pin, the probability is unity that the real number I get will be uncomputable. Okay? So with probability 1, real numbers are computable. Now that's sort of annoying if you have the attitude that if you can't compute a real number, why should I believe it exists? Okay? So let me go on a little bit. How am I doing with time? Am I over, under? I'm halfway. Oh, maybe I'm going too fast. I can slow down now. Another notion that I like to talk about, which is a notion of mine, is this notion of an algorithmically irreducible real number. Algorithmically random or irreducible might be a safer word because random has too many meanings. Irreducible real. Random in quotes. Irreducible might be better. Incompressible real. Now, what is that notion? Well, the idea is lack of structure, and the way you define it is you look at the first n bits of this real number. They're always between 0 and 1. You look at the first n bits of the real number, and you ask yourself, what is the size of the smallest computer program that calculates those first n bits? Okay? So, and the idea is, if this is large, very close to n, you say that the bits of that real number have no structure or pattern, no algorithmic structure or pattern. And if this is very small, the size of the smallest program that calculates the first n bits as a function of n, then that real number is atypical, has a lot of structure or pattern. So let's look at pi or e. Well, pi or e are computable reals, so there's a program that given n calculates the first n bits. And that program is a fixed part, and all you need to tell it is what n is. So in other words, basically, for a computable real number, something like log 2n plus c bits is enough to calculate the first n bits of that number, right, for all n. This is the algorithm for pi or e, and this is the number of bits you need to say how many bits you want. So computable reals have very low program size complexity. And however, you can show and I need something called self-delimiting programs, which I don't want to talk about. To get the right definition of this concept would take a little bit of time, so I won't take the time. There is a definition of algorithmically random real number which goes like this. It says the program size complexity, the number of bits of information you need to tell a computer how to calculate the first n bits of this number, is very high. And it's greater than n minus. There is a C such that for all n, this is the case. Okay? This is how you define a notion of lack of structure in the bits of a real number. And this definition is chosen in such a way that with probability 1, a real number will have, its binary expansion will have this property. Okay? Which means most real numbers have no structure. You can't compress the information in the first n bits into a computer program which is significantly smaller. You might be able to compress it a little bit, but essentially not much below n. Okay? So this is a definition of lack of structure in a real number, and it's a definition which is good, because if you have a definition of a random real, you want most reals to be random. And this definition has the probability the real number satisfies this with probability 1. Okay? Now, let's look at this real number. And I happen to have one that I call omega, which I'll talk to you about in a moment. It's the halting probability of a computer. Turing talked about the halting problem, and I talk about the halting probability. But let me first talk about an algorithmically random real number and about an uncomputable real. Let's say instead of trying to compute it, I should slow down. Mil disculpas, perdónenme, I'm going too fast. Désolé. Let's say instead of trying to calculate the bits of a real number, I'm trying to prove what the bits are using a formal axiomatic system, which is a formal mathematical system where you give the axioms, use symbolic logic. It's an artificial language, and in fact, there's a proof-checking algorithm, for example. The grammar is a formal grammar. This is an idea that goes back to Hilbert. Actually, it goes back to everyone who's worked on symbolic logic. But Hilbert stated about a century ago pretty clearly this idea of removing all uncertainty from math by going to an extreme and having an artificial language for doing mathematics, where you give the axioms and all the rules of inference and everything explicitly. Use symbolic logic. You don't use a normal language. You use an artificial language with precise rules. And the point of this, according to Hilbert, was to remove all uncertainty from math, and that there should be mechanical referees. He wouldn't put it that way. You know, one of the problems with writing a paper is the referees take 3 years, right, in math at least. But it would be nice if you could just give the proof to a computer program which checks that the proof obeys the rules. Well, the problem with that is the proof, you'd have to put in all the details into the proof and then change it from Portuguese or English to some artificial language, like a computer programming language. It would probably be horrid. But the idea is not to actually do this, but to do it in principle, take all of math and put it into one of these formal axiomatic systems. Now, if you could do that, one of the consequences that Turing points out in 1936, but I suspect Hilbert knew already, is that if you could put all of math into one of his formal axiomatic systems, there would be a mechanical procedure that would be very slow, but it would produce all the theorems one by one, by running through all possible proofs, either with a tree search or by all possible proofs in size order as character strings, and you just check which ones obey the rules. So you look through all possible proofs systematically, and you get all the possible theorems. Okay, and this was in Turing's paper, and in 1943, Emil Post actually has a wonderful paper where he abstracts that notion. He calls it a recursively enumerable set, and now it's called a computably enumerable set. And this is the essence of this idea of an absolutely rigorous formal mathematics that Hilbert thought was a possibility.